As mentioned in the conclusion of the last module, we will be looking at a generalization of Bucci automata. In this module, they are called generalized Bucci automata. So consider this Bucci automaton. It has three states, Q0, Q1, Q2. On an A, Q0 on an A keeps looping at Q0. When there is a B, from Q0 the automaton goes to Q1 and immediately it has to see an A. If there is a C, then it goes to Q2 and immediately it has to see an A. So how do the words accepted by this automaton look like? It reads some number of A's followed by either a B or a C. After that, immediately an A follows, and this pattern keeps repeating infinitely often. So the language of this automaton is A star, B plus C followed by an A, this whole thing par omega. Note that one is not required to see both B and C infinitely often. Even the word A, B, A, B, A, B, A, B, A, B is accepted by this Bucci automaton. Because the acceptance condition says that as long as one of these states occurs infinitely often, the word should be accepted. Suppose we want the Bucci automaton for the subset of this language where both B and C occur infinitely often. In particular, words like this should be eliminated. Both B and C should occur infinitely often. So essentially, the states Q1 and Q2 should occur infinitely often. This kind of a condition cannot be given directly for Bucci automata because you can just say that the set of accepting states is Q1, Q2, and it does not enforce that both Q1 and Q2 should occur infinitely often. So in order to build an NBA for this, we have to come up with a completely different set of states and transitions. Instead of doing that, we will give a different accepting condition. We give this automaton, we do not mark any state as accepting, and instead we give an accepting condition like this. It's going to be a set of sets. So the first set of states is Q1 and then there is a set Q2. This means that a run is accepting if it visits both Q1 and Q2 infinitely often. Instead of giving one set, we are giving a set of sets. Here each set is a singleton. So a run is accepting if it infinitely often sees states from both these sets. So in particular, this condition will tell you that a run is accepting if both Q1 and Q2 are seen infinitely often on this automaton. This kind of an automaton with this accepting condition is called generalized non-deterministic Bucci automaton. You have the same structure as an NBA, states, transitions and initial state, just that instead of giving a set of accepting states, we give a set of sets. And the condition is that the run is accepting if it contains at least one element in each set. Let's see one more example. Suppose this is the automaton structure. We just extended it from before. There is one more alphabet D. Now we want a generalized Bucci automaton for the subset of A star, B plus C plus D, A par omega, where D should occur infinitely often and either B or C occurs infinitely often. So a word is accepted if it contains infinitely often the letter D and one of either B or C occurs infinitely often. For example, CA will not be accepted because D does not occur infinitely often. Suppose we look at DA, BA, DA, BA and so on, that will be accepted because D occurs infinitely often and B also occurs infinitely often. How do we give our accepting condition for this? We want Q3 to occur infinitely often and either Q2 or Q1 should occur infinitely often. So we give the condition like this. The condition consists of two sets. The first set is Q3 and the second set is Q1, Q2. This says that the run is accepting if Q3 occurs infinitely often and one of either Q1 or Q2 occurs infinitely often as well. So this is what a generalized Bucci automaton is. It consists of states, transitions, initial states as in an NBA, just that the accepting condition is given as a set of sets. So each set consists of states. For example, here F1 is the set Q3, F2 is the set Q1, Q2. You can give a finite number of such sets and the run is accepting if some state from each of these, note from each of the Fi occurs infinitely often. So here the run would be accepting if a state from each of F1 and F2 occurs infinitely often. Since F1 has only Q3, Q3 should occur infinitely often and either Q1 or Q2 occurs infinitely often. This is what a generalized Bucci automaton is. It just modifies the accepting condition to write properties in a more convenient manner. The question is, by doing this, can we accept languages that a normal Bucci automaton cannot? Let us see. Look at this GNBA, Q0, CA, BAA. This is the same GNBA as before. We want to see both C and B infinitely often. The accepting condition consists of the set Q1 and the set Q2. We will now try to convert this GNBA into a standard non-deterministic Bucci automaton. What do we want to get? We want to say that every run here should visit both Q1 as well as Q2 infinitely often. How do we try to make an NBA do this? We consider an NBA with more states. So for each state, have a flag 1 and 2. This corresponds to two sets, F1, F2. So have 1 and 2. So you have Q01, Q21, Q11 and Q02, Q12 and Q22. The initial state is going to be Q01. This 1 signifies that the automaton is waiting to see a state in F1. 2 signifies that the automaton is waiting to see a state in F2. Now how do we draw the transitions? As long as there are transitions between states which are not in F1, just add them. So here Q0, the automaton is waiting to see a state in F1. From Q0 on a C, it goes to Q2. Since Q2 is not in F1, the transition out of Q2 goes back to Q0 with 1 itself. We are yet to see a state of F1. Now on a B, Q0 goes to Q1. Now see that Q1 is a state in F1. So the outgoing transition from Q1 will actually jump to Q0 with the 2. From this state, you should be trying to see a state in F2. Okay, so now see, Q0 on a B goes to Q1, so Q0 2 on a B goes to Q1 2. Since Q0 is not in F2, you just keep staying in the 2. Similarly, since Q1 is not in F2, the transition out of it goes to a state with the flag 2. Now Q0 on a C goes to Q2 2. Q2 is in F2. So once you see Q2, the outgoing transition should go back to this state. Suppose I do this. This will mean that we have seen a B, A, C, A. Starting from this state, if you ever manage to come back to this state, that is possible only if you have seen Q2. Otherwise, there is no way you can come back to this state. And this will be made the accepting state. You look at F1, you look at the states in F1, there is only Q1, and those states with the one copy will be made accepting. Consider this to be a standard NBA. Look at accepting runs. Look at runs which visit this state infinitely often. B, A, B, A, C, A, C, A, B, and so on. If a run visits this state infinitely often, then both B and C would have occurred infinitely often. For example, if it is the case that you are always here, there is no B after some time, then you would not be visiting this. Similarly, if there is no C after some time, then that is possible only if you keep looping around here. As you see, if you wanted an NBA for the same property, you should have given an NBA with more states. On the other hand, the GNBA has only 3 states, just that the accepting condition is modified. A generalized non-deterministic Bussy automaton can be considered as a syntactic sugar. Let us see how this example works. So this is a GNBA and the set of accepting sets is Q3, Q1, Q2. So a run is accepting if it visits Q3 infinitely often and one of Q1 or Q2 infinitely often. How do we construct an NBA? Multiply the states by 2 because there are 2 sets here. As long as you are here, you want to read some accepting state in the first component, which is Q3. So the other transitions are the same as before. At Q3, once you reach Q3, the outgoing transition jumps to the second copy. Here, as long as you are not in Q1 or Q2, you keep staying here. Once you reach either Q2 or Q1, because Q1, Q2 are in F2, once you are here, the outgoing transitions on an A go back to Q0. You have to jump to the first copy because you have seen Q1 and Q2. The construction is simple. You multiply the automaton by 2 in the sense that for every state here, add a state Q01 and Q02. Similarly, Q11, Q12, Q21, Q22, Q31, Q32. All outgoing transitions from the first set in the first copy go to the second copy, and all outgoing transitions from the states in F2 which are in the second copy go back to the first copy. Which will be the accepting state? You look at the first component, which is Q3, and Q3, 1 will be the accepting state. If you see a run which visits Q3 infinitely often, Q3, 1 infinitely often, you will notice that it is possible only if D occurs infinitely often, which means Q3 occurs infinitely often, and one of either Q2 or Q1 occurs infinitely often. This is the standard NBA corresponding to this GNBA. Essentially, this is what we wanted to show in this module. There is something called Generalized Bucci Automata. It has the same syntax, states, transitions, initial states as in an NBA. The only modification is in the accepting condition. Instead of specifying some states as accepting, you give a set of states like this. In fact, it's a set of sets of states. F1 consists of some set of states, F2 consists of some set of states, similarly Fk consists of some set of states. A run on a word is accepting if some state from each of these Fi's occurs infinitely often. We saw two examples. Please go through them. We have shown on the examples that those GNBAs can be converted to a standard NBA. This is true of every GNBA. Every GNBA can be converted to an equivalent NBA, and the construction is similar to the examples. If you have k sets, you need to multiply by k. In the sense, for every state here, you need to have k copies. As soon as you start with the first copy, as soon as you see some state in F1, you jump to the second copy, you keep doing the transitions there. As soon as you see a state of F2, you jump to the third copy and so on. Once you are in the kth copy and you see some state in Fk, you jump back to the first copy. And the states in the first copy, which are in F1, will be called the accepting states. This is how you get an NBA out of a GNBA. As long as you know the syntax of GNBA and as long as you know that GNBA can be converted to an NBA, it is sufficient for this course. The exact details of the construction are not necessary.